I'm MaxSilva-Feaver. I'm a third-year graduate student here at UC San Diego, from Santa Barbara, California, and I'm working on the Readout and Detectors for the Simons Observatory. I started doing physics in high school. Was in an engineering academy, robotics academy, and had a very enthusiastic physics teacher from that academy. And I think it was sort of through him that springboarded me into continuing in undergrad at Santa Clara University. Then I had a great undergraduate research advisor that introduced me to the world of low temperature detectors and sensors. And that sort of was my route into cosmology and to CMB. San Diego's been great. The town is very laid back. It reminds me a lot of my hometown of Santa Barbara. And the university is really exciting. You know, we have Qualcomm here, so we have the electrical engineering department's really great, and I know that it's been cool the legacy history Polar Bear has had collaborating with folks in the antenna design here. And there's a vibrant group of people, both in theory and experiment, for the CMB here, from undergraduate all the way through faculty, postdocs. We have a big group here, so it's very exciting to work with all those folks. And then also just being in the astrophysics building is exciting too. Having folks in X-ray astronomy and optical astronomy, all a couple doors down. It's been a really great experience for me, I think. So I'm particularly working on the readout system for the camera. So we have both our homemade custom camera pixels that we call transition edge sensors, but then those are cooled down to 100 thousandths of a degree, a tenth of a degree above absolute zero. So very, very cold operation. And we need all of our electronics, at least the first stage of electronics, all to operate at that same temperature. So we also custom make all these electronics. And we're trying to make the most precise camera possible. So every single pixel has to have very high fidelity. And so that means that we don't want, at least the very early stages of the electronics need to be very low noise, very precise. And so this system we're deploying for Simons Observatory to achieve this is called microwave multiplexing, which was originally thought up around the 2010-2011 timeframe. This will be the first time we're going to deploy this system in scale at this 2,000 time multiplexing factors. The big advantage of microwave multiplexing is that it will be able to read out many camera pixels with a single pair of wires. So we're shooting for Simons Observatory to reach a factor of 2,000, and previously demonstrated with microwave multiplexing is been with bicep Keck, which at most has reached about a factor of 500. And so we're really going to push the limit of this technology, and so it's very exciting to be working on this. But there's tons of challenges. So we're dealing with developing a whole new set of digital electronics that sit outside of the receiver. We're dealing with fabricating more precise microfabricated resonators that sit actually at the 10th of a Kelvin stage right at our camera. And all of the integration into these huge receivers for Simons Observatory is a huge effort. So integrating with the camera array, integrating with all of the other cabling, there's tons of potential for failure points and added noise or error in the measurement. And so my job so far has been that integration level for Simons Observatory, that sort of testing of all of the stages of components that will be required to integrate this new technology of microwave multiplexing at the huge multiplexing factors of 2,000 pixels per wire into the Simons Observatory cameras. And when I talk about readout, I basically mean
if this right here is the detector array, so the lenslet couples and the actual pixels, then all of this stuff back here and all of these cables coming out and attachments, this is all readout. So this is the readout we'll be using for Simon's array, or polar bear, which is the digital frequency domain multiplexing. And one of the benefits of moving to the Simon's Observatory readout system, the microwave multiplexer, is that, I mean, everything becomes contained in one nice tight module that we call the microwave multiplexing board, and it makes the complexity and sort of the space requirements for the readout behind the detector much less. And so that's one of the huge motivations for moving to microwave multiplexing is all of this that's required to get the detectors read out in the previous generation experiments. We'll try and simplify and for the Simon's Observatory, and hopefully demonstrate a better way to do it for the future experiments.
So I still have at least 3-4 years left in graduate school, planning to try and stay through seeing some of the initial small aperture telescope cameras deployed to Chile, and to get to help with the integration of the readout into the real cameras, and deal with all the physical hardware issues we're going to have along the way. After, I hope to continue working in the area of low temperature detectors, either in CMB applications, or there's lots of very interesting applications in X-ray astrophysics. And so I'd like to continue working with the same sort of very precise detectors in the wider scope of low temperature detectors for astrophysics.